Welcome to Astrum Discovery Network, where we journey together into the deepest mysteries that define the very fabric of our reality. Look around at the stars, the planets, and the galaxies that fill the vast, silent darkness of our observable cosmic neighborhood. Everything you can touch, see, and feel is made of matter, a substance that seems to be the only game in town. But physics tells us that for every piece of matter created, there should have been an equal counterpart, known as antimatter. If these two opposites meet, they annihilate each other instantly, leaving behind nothing but a burst of pure, intense energy. To understand this cosmic imbalance, we must travel back to 17th century Venice, where the obsession with balance first truly began. Meet Santorio Santorio, a dedicated physician who spent 30 years of his life obsessed with measuring the balance of nature. He weighed every morsel of food he ate and every drop of liquid he drank, seeking a perfect input and output. He even slept on his scale, determined to account for every single ounce of matter that passed through his biological system. Santorio discovered that the weight of his waste was less than the food he consumed, leading to the concept of metabolism. He realized that matter wasn't disappearing, but changing form into invisible perspiration, maintaining a hidden balance within the physical world. This pursuit of balance led to the law of conservation of mass, stating that matter is neither created nor destroyed. For centuries, scientists believed that the universe was a closed system, where the total amount of stuff remained exactly the same. Then came Albert Einstein, who revolutionized our understanding by revealing that mass and energy are actually two sides of the same coin. His famous equation proved that matter could be turned into energy, and conversely, pure energy could be frozen into matter. Enter Paul Dirac, a brilliant but reserved physicist who took Einstein's work and combined it with the new quantum mechanics. Dirac was searching for a beautiful equation that could describe the behavior of electrons moving at close to the speed of light. When he solved his equation, he encountered something strange. The mathematics provided two distinct solutions instead of just one single answer. Just as the square root of 4 can be 2 or minus 2, his equation predicted a particle with negative energy. Dirac realized this wasn't a mistake, but a revelation. For every particle, there must exist a mirror image, called an antiparticle. At first, the scientific community was skeptical, finding it hard to believe in a shadow world of matter we had never seen. But in 1932, Carl Anderson pointed his cloud chamber at the sky and captured the first evidence of antimatter. He saw a particle that looked exactly like an electron, but curved in the opposite direction within a strong magnetic field. It was the positron, the anti-electron, predicted by Dirac, proving that antimatter was not just math, but a physical reality. This discovery leads us back to the Big Bang, the moment when all energy was converted into matter and antimatter. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter in the beginning. In that dense, hot soup, matter and antimatter waged a war of mutual destruction, annihilating each other upon every contact. If the symmetry had been perfect, the universe would be empty today, filled only with light and absolutely no stars. But something incredible happened. A tiny imbalance allowed a small fraction of matter to survive the great cosmic purge. For every billion pairs that destroyed each other, just one single particle of matter managed to escape the fiery death. That one survivor in a billion is what makes up every galaxy, every star, every planet, and every person today. To find the cause of this imbalance, we look to Xianxun Wu, a brilliant experimental physicist known as the First Lady of Physics. She conducted an experiment cooling cobalt-60 atoms to near absolute zero to see if the universe distinguished between left and right. Shockingly, she found that the particles preferred one direction over the other, proving that the universe is not perfectly symmetrical. This was parity violation, a discovery that shattered the long-held belief that nature behaves exactly the same in a mirror. Later, scientists discovered CP violation, showing that matter and antimatter behave slightly differently, hinting at why we are here. However, known physics isn't enough to explain the imbalance, leading us to suspect the ghostly particles known as neutrinos. Deep underground detectors are now hunting for clues, hoping neutrinos hold the final secret to the origin of our material universe. We exist only because of a fundamental flaw in the mirror of perfection, a lucky break in the cosmic laws. Thank you for joining Astrum Discovery Network on this journey. Subscribe to explore more secrets of the cosmos. Goodbye for now. As we gaze into the night sky, we remember that our very existence is a testament to a cosmic anomaly. The dance of particles continues, a silent ballet that has been performing since the very first moment of time began. Every chapter of physics we uncover reveals deeper questions, inviting us to keep searching for the ultimate truth of reality. Curiosity drives us forward, pushing the boundaries of what is known and venturing into the vast unknown of the universe. Machines, like the Large Hadron Collider, help us recreate the conditions of the early universe to study these fundamental particles. Dedicated researchers spend their lives analyzing data, looking for the tiny deviations that could explain everything we see around us. The cosmic microwave background radiation provides a snapshot of the infant universe, holding secrets of the matter and antimatter war. We are small in the grand scheme, yet our minds are capable of grasping the mechanics of the entire cosmos. Each sunrise reminds us of the energy that powers our world, energy that follows the same laws as the stars. The carbon in our bodies was forged in the hearts of dying stars, survivors of the ancient cosmic matter battle. Our civilization is built on utilizing matter and energy, manipulating the very substances that were born from the Big Bang. Future generations will continue this quest, asking new questions and finding answers that we cannot even imagine right now. Galaxies like Andromeda are racing towards us, reminding us that the universe is dynamic, ever-changing, and full of surprises. Even in the extreme gravity of black holes, the laws of quantum mechanics and relativity struggle to find a harmony. Looking back through time, we see a history written in light and gravity, a story of survival against the odds. Quarks bind together to form protons and neutrons, the building blocks of the atomic nucleus that gives matter its mass. Gravity sculpted the leftover matter into the structures we inhabit, creating safe harbors in the vast emptiness of space. Life itself is a complex arrangement of matter, dependent on the stability of protons that have existed for billions of years. The information in our DNA relies on the chemical bonds of matter, stable only because antimatter is not present here. Our probes travel through the void, never encountering clouds of antimatter, confirming that our region of space is matter-dominated. If there were antimatter galaxies, we would see massive radiation from the boundary where they touch matter galaxies, but we don't. Teachers explain these concepts to students, passing the torch of knowledge and inspiring the next wave of scientific discovery. In labs across the world, the hunt for new particles continues, pushing the limits of technology and human ingenuity daily. Quantum computing may one day help us simulate the early universe with precision, unlocking secrets that remain hidden today. The beauty of the night sky is a constant reminder of the lucky accident that allowed matter to win the war. Our planet is a sanctuary of matter, a fragile blue dot protected by the vacuum of space from any antimatter. Supernovae spread heavy elements across the cosmos, enriching the universe with the materials needed for rocky planets and life. Comets carry water and organic compounds, messengers from the dawn of the solar system, delivering ingredients for life to Earth. Telescopes like James Webb look back in time, trying to see the very first galaxies that formed after the Dark Ages. Cosmic dust obscures our view, but infrared light penetrates through, revealing the hidden nurseries where new stars are being born. Gravitational waves give us a new way to listen to the universe, detecting collisions of black holes and neutron stars. Neutron stars are so dense that a teaspoon of their material would weigh billions of tons on our planet Earth. The aurora borealis shows us the interaction of charged particles with our magnetic field, a beautiful display of physics. This magnetic shield protects us from solar wind and cosmic rays, some of which are actually high-energy antimatter particles. The Sun constantly streams particles towards us, a reminder of the nuclear fusion reactor that sustains all life here. As the Sun sets, we reflect on the balance of day and night, a cycle that governs our biological clocks. Our bodies are tuned to the rhythms of the cosmos, connecting us deeply to the physical laws of the universe. Life creates order from disorder, temporarily defying entropy by using energy to build complex structures like cells and tissues. But eventually, everything returns to dust, following the second law of thermodynamics, which dictates the flow of time itself. Time moves forward, driven by the expansion of the universe and the increasing disorder of energy within the system. The universe is getting bigger and colder, stretching the light from distant galaxies into the infrared part of the spectrum. Dark energy pushes the galaxies apart, a mysterious force that makes up most of the energy budget of the cosmos. Visible matter is only 5% of the universe. The rest is dark matter and dark energy, completely invisible. Dark matter holds galaxies together, providing the gravitational glue that prevents stars from flying off into the intergalactic void. When galaxies collide, dark matter passes through like ghosts, while ordinary gas clouds crash and heat up to extreme temperatures. X-ray telescopes reveal the hotspots of the universe, showing us where matter is being accelerated to incredible speeds. Matter falling into black holes forms accretion disks, shining brightly before crossing the event horizon into the point of no return. The event horizon marks the boundary of our knowledge, where space and time are distorted beyond all conventional human understanding. Stephen Hawking predicted that black holes emit radiation, slowly evaporating over eons until they disappear in a final flash. In the distant future, black holes may be the last sources of energy in a dark and dying universe. The heat death of the universe is a somber prediction, but it is trillions of years away from now. For now, we live in the stelliferous era, the age of stars, where light and life are possible and abundant. We should cherish this time, exploring and understanding the universe while the stars still shine brightly in our night sky. Exploration is in our DNA. We are stardust that has become self-aware, looking back at the universe that created us. Our brains are the most complex structures in the known universe, capable of imagining worlds that do not yet exist. Through art and science, we express our wonder and gratitude for the existence of matter and the beauty of reality. Sculptors shape matter into forms that evoke emotion, proving that dead atoms can be arranged to convey deep meaning. Architects build structures that defy gravity, using the strength of chemical bonds to create shelter and monuments for humanity. Bridges connect us, overcoming physical barriers and uniting people, just as the fundamental forces unite particles into coherent matter. The internet connects our minds, transmitting information as pulses of light and electricity across a web of physical cables. Data is the new gold, but it relies on physical storage, magnetic domains on hard drives, or trapped electrons. Data centers hum with energy, processing the collective knowledge of our species and searching for patterns in the noise. Artificial intelligence helps us process vast amounts of data, acting as a partner in our quest to understand physics. Robots extend our reach to planets like Mars, analyzing soil samples to see if matter there hosted life. Mars is a rusty world, its iron oxide surface telling a geological history of water, atmosphere, and climate change. We dream of terraforming other worlds, transforming their matter to create habitable environments for future human colonies and expansion. The International Space Station is our foothold in the void, a laboratory where we study how matter behaves in microgravity. Astronauts experience the universe differently, seeing the fragility of Earth's atmosphere against the stark black backdrop of space. From a distance, borders vanish, and we see only one planet, a shared home made of precious, surviving matter. We must protect this matter, recycling resources and minimizing waste, mimicking the efficiency of nature's own cycles and systems. Renewable energy captures the flow of nature, sunlight and wind, to power our civilization without destroying our environment. Wind turbines spin, converting the kinetic energy of moving air molecules into electricity that lights up our modern homes. Solar panels absorb photons from the sun, knocking electrons loose to create a current, a direct harness of stellar power. Hydroelectric dams use gravity and water to generate power, demonstrating the transformation of potential energy into useful electrical energy. Fusion power offers the promise of clean, limitless energy, replicating the process that powers the sun here on Earth. Inside a tokamak, magnetic fields hold plasma hotter than the sun, trying to force hydrogen nuclei to fuse together. Mastering fusion would be a turning point, giving us the energy to explore the stars and protect our planet. Interstellar travel requires exotic propulsion, perhaps even using antimatter as a fuel source, due to its high energy density. An antimatter engine would be the most efficient possible, converting fuel entirely into thrust with zero wasted mass. Currently, making antimatter is incredibly expensive and slow, requiring massive particle accelerators to produce just a few tiny nanograms. We store antimatter in magnetic traps, keeping it away from the walls of a container to prevent instant annihilation. Antimatter has medical uses too. PET scans use positrons to detect cancer, saving lives with antimatter technology every day. In a PET scan, a radioactive tracer emits a positron, which annihilates with an electron, signaling the tumor's location. This allows doctors to see inside the body without surgery, a peaceful application of the destructive power of annihilation. Science transforms dangerous phenomena into tools for healing, showing the dual nature of knowledge and its application in society. From the smallest cell to the largest galaxy, the same laws of physics apply, unifying all of nature's scales. Crystals show the order of atoms, repeating patterns that create beauty and strength. used in technology from watches to computers. Silicon chips are the brains of our devices, relying on the precise manipulation of electrons to process logic and data. Clean rooms for chip manufacturing are some of the purest places on Earth, free from dust that could ruin circuits. Nanotechnology builds materials atom by atom, creating super strong and light materials that could revolutionize construction and aerospace industries. Carbon nanotubes are stronger than steel and conduct electricity better than copper, promising a future of incredible technological advancements. One day, we might build a space elevator using these materials, making travel to orbit cheap and accessible to all. Imagine a busy port in orbit, where ships depart for the Moon and Mars, carrying passengers and cargo daily. Asteroid mining could provide the resources we need, protecting Earth from the environmental damage of industrial mining operations. The asteroid belt is a treasure trove of metals and water, waiting for brave pioneers to harvest its vast riches. Robotic ships will likely be the first miners, enduring the harsh radiation and long travel times of deep space. A space economy will emerge, trading goods and services beyond the atmosphere, creating new wealth and opportunities for humanity. Transactions might be handled by secure digital ledgers, ensuring fair trade across the vast distances of the solar system. As we expand, our society will evolve, adapting to new environments and challenges, but always rooted in our humanity. Education will remain key, teaching the next generation the physics and ethics needed to wield such power responsibly. Knowledge must be preserved and shared, ensuring that the mistakes of the past are not repeated in the future. Our culture, music, and stories are as important as our technology, defining who we are as we travel the stars. Imagine a concert on the Moon, music echoing in a pressurized dome, with the Earth hanging beautifully in the sky. New sports will be invented for zero gravity, utilizing the unique physics of space to create exciting athletic challenges. Life in space will become normal, with people living, working, and raising families on rotating habitats, providing artificial gravity. Hydroponic farms will feed these colonies, recycling water and nutrients in closed loops to ensure sustainability and survival. Plants provide oxygen and mental well-being, a touch of green earth in the sterile metal environments of space stations. Water is precious in space, every drop reclaimed and purified, teaching us the value of this resource back on Earth. Seeing Earth from space inspires a desire to protect it, realizing it is the only natural paradise we have. Space exploration fosters peace, as nations must work together to survive the hostile environment and achieve common goals. Diplomacy and science go hand in hand, building bridges between cultures through the universal language of mathematics and physics. Perhaps one day we will fly a flag of Earth, representing a united species exploring the cosmos as one. A fleet of ships departing for the stars would be the culmination of thousands of years of human curiosity. We have explored all the planets in our solar system, but there are still many moons and asteroids to visit. Europa may hide a liquid ocean under its ice, a prime candidate for finding alien life within our reach. Robotic submarines could melt through the ice to explore these dark waters, searching for thermal vents and microbes. Titan has lakes of methane and a thick atmosphere, a strange chemical laboratory that mimics early Earth conditions. Drones can fly easily in Titan's low gravity and dense air, mapping the surface of this mysterious orange moon. Beyond Neptune lies the Kuiper Belt, home to Pluto and thousands of icy worlds that preserve the solar system's history. New Horizons showed us Pluto's heart, a geological feature that proved even distant dwarf planets are active and dynamic. Far further out is the Oort cloud, a spherical shell of comets that marks the true edge of our system. The nearest star, Proxima Centauri, is 4 light-years away, a distance that challenges our current propulsion technologies. Proxima b is an Earth-sized planet in the habitable zone, a tantalizing target for the first interstellar mission. Projects like Breakthrough Starshot aim to send tiny laser-pushed sails to reach these stars within a human lifetime. Riding a beam of light, these probes could fly at 20% the speed of light, reaching Alpha Centauri quickly. It would take 4 years for their pictures to travel back to Earth, a long wait for a glimpse of another world. But the wait would be worth it, confirming if we are truly alone or if the universe is teeming with life. Finding alien life would change everything, forcing us to rethink our place in the cosmos and our philosophy. Communicating with another intelligence would be the greatest challenge, requiring a common language based on math and science. We listen with radio telescopes, scanning the frequencies for any pattern that stands out from the cosmic background noise. The search for extraterrestrial intelligence is a long shot, but the implications of success are too huge to ignore. The Drake equation estimates the number of civilizations, but many variables remain unknown, leaving us with only guesses. The Great Silence is puzzling. If life is common, where is everybody? This is the Fermi paradox. Perhaps there is a great filter, a challenge so difficult that most civilizations fail to survive it and go extinct. Nuclear war, climate change, or AI could be our filter. We must navigate these dangers carefully to survive. Choosing peace and sustainability is not just moral, it is a survival strategy for our species on a cosmic scale. We teach our children to value life and the planet, hoping they will make better choices than we have. The tree of life is resilient, having survived 5 mass extinctions on Earth, and it will likely survive us too. Evolution is slow but relentless, constantly adapting life to the changing conditions of the environment over millions of years. Humans may evolve too, or modify ourselves with technology, becoming a new species adapted for life among the stars. Merging with machines could enhance our intelligence and durability, allowing us to process information at the speed of light. Some dream of uploading consciousness to computers, achieving digital immortality and freedom from the limitations of a biological body. In virtual worlds, we could live out any fantasy, creating universes of our own design with their own physics. This raises the question, are we already living in a simulation? Is our reality just code running on a computer? If physics is computable, then the universe is mathematical, and the distinction between reality and simulation becomes very blurry. Mathematicians explore these abstract realms, finding truths that exist independently of the physical world we observe around us. Fractals show infinite complexity from simple rules, mirroring how complex life arises from simple physical laws and constants. Chaos theory teaches us that small changes can have huge effects, the butterfly effect that makes prediction difficult. We can predict the motion of planets for centuries, but cannot predict the weather next week with perfect accuracy. Nature is a mix of order and chaos, predictable cycles and unpredictable outbursts that keep the universe interesting. Like waves on the ocean, energy moves through the universe, transferring power without necessarily moving matter over long distances. Sound requires a medium like air, but light can travel through the vacuum, allowing us to see the stars. A prism splits white light into a rainbow, revealing the spectrum that tells us what stars are made of. Spectroscopy is our key to the cosmos, decoding the fingerprints of elements light years away from our laboratories. Redshift tells us how fast objects are moving away, the primary evidence for the expansion of the universe. Edwin Hubble discovered this expansion, transforming our view of the universe from static and eternal to dynamic and evolving. Georges Lemaitre proposed the Big Bang theory, suggesting everything started from a primeval atom of incredible density. The discovery of the cosmic microwave background confirmed the Big Bang, earning Penzias and Wilson a Nobel Prize. They thought it was pigeon droppings on their antenna, but it was actually the afterglow of creation they detected. Serendipity often leads to great discoveries. Looking for one thing, scientists stumble upon something even more important. Like Fleming discovering penicillin, astronomers often find the unexpected, rewriting textbooks with their accidental observations. Radio astronomy opened a new window, showing us pulsars, quasars, and other high-energy phenomena invisible to optical telescopes. Pulsars are cosmic lighthouses, spinning rapidly and sending beams of radiation that sweep across the Earth with precision. We use pulsars to map our location in the galaxy, a cosmic GPS for future interstellar travelers. The Voyager Golden Record contains a map using pulsars, telling any aliens where to find our home planet. It also carries sounds of Earth, greetings in many languages, and music, a time capsule of humanity. Carl Sagan championed this message, believing in the importance of reaching out to the cosmos with hope. He famously called Earth the pale blue dot, a speck of dust suspended in a sunbeam. This perspective breeds humility, showing how small our conflicts are against the backdrop of the immense universe. We are one species sharing a small planet, and we must learn to live together or perish together. The future is not written, it is ours to create, through our choices, our science, and our compassion. We also explore our own oceans, the inner space that is just as mysterious as the outer space. Deep-sea creatures live in extreme pressure and darkness, showing life's adaptability to even the harshest conditions. Hydrothermal vents might be where life began, fueled by chemical energy from the Earth's interior rather than sunlight. Understanding life's origins helps us know what to look for on other worlds like Enceladus or Europa. Carbon chemistry is versatile, forming the backbone of DNA, proteins, and all the molecules essential for biology. Chemists synthesize new compounds, creating medicines and materials that improve our quality of life and longevity. Vaccines protect us from invisible enemies, a triumph of science over disease that has saved billions of lives. Electron microscopes let us see viruses, visualizing the enemy to defeat it with precise molecular engineering tools. CRISPR technology allows us to edit genes, curing genetic diseases, but raising ethical questions about designer babies. We must navigate these ethical dilemmas carefully, ensuring technology serves humanity without compromising our values or dignity. Discussions involve scientists, philosophers, and the public, creating a consensus on how to move forward responsibly. Democracy allows people to have a say in scientific policy, funding the projects that matter most to society. Investing in basic research pays off decades later, often in ways that were impossible to predict at the start. GPS relies on Einstein's relativity. Without correcting for time dilation, your navigation would fail within minutes. Your smartphone contains more computing power than NASA had when they sent men to the moon. Technology connects us instantly, creating a global village where ideas spread at the speed of light. But misinformation also spreads. Critical thinking and scientific literacy are essential to navigate the modern information landscape. We must verify facts, relying on evidence and peer review rather than rumor or wishful thinking. The scientific method is our candle in the dark, a systematic way to find truth and correct our errors. Galileo faced persecution for the truth, reminding us that science often challenges established power and comfortable beliefs. Academic freedom allows scientists to pursue the truth wherever it leads, without fear of censorship or retribution. Libraries are temples of knowledge, preserving the wisdom of the past for the benefit of the future. Digitization makes this knowledge accessible to anyone with an internet connection, democratizing learning across the globe. A child in a remote village can now learn physics from top professors, unlocking potential that was previously wasted. The next Einstein or Curie could come from anywhere, provided they have access to education and opportunity. Diversity in science brings new perspectives, helping to solve problems that a homogeneous group might overlook. Women have made huge contributions, often unrecognized, but history is now being corrected to honor their work. Marie Curie is the only person to win Nobel Prizes in 2 different scientific fields, physics and chemistry. Her legacy inspires girls everywhere to pursue science, breaking down barriers and shattering glass ceilings. Science is a global endeavor, transcending borders and politics to unite humanity in the pursuit of knowledge. Conferences bring minds together, sparking collaborations that lead to breakthroughs in medicine, energy, and space exploration. When a discovery is announced, the whole world celebrates, sharing in the triumph of human understanding. The Nobel Prize recognizes these achievements, highlighting the importance of intellectual effort and its benefit to mankind. But the real work happens in quiet labs late at night, driven by passion rather than the hope of fame. The thrill of figuring out how the universe works is the greatest reward for any physicist. That eureka moment, when the pieces fit together, is a feeling of pure joy and connection with the cosmos. Sharing that knowledge completes the cycle, enriching the collective mind of humanity and paving the way for progress. Textbooks are updated, old theories discarded or refined, as we march ever closer to the ultimate truth. There is always a new horizon, a new mystery waiting to be solved, ensuring science never ends. What is dark matter? What happened before the Big Bang? These questions keep us up at night, but we dream of answers, and with time and effort, we will find them, just as we found the positron. Perseverance is key. The road to discovery is paved with failure, but each failure teaches us something new. Trial and error is the heartbeat of progress, refining our ideas until they stand the test of experiment. And when we succeed, we push the human race forward, expanding our capabilities and our understanding of existence. From Santorio's scale to the Large Hadron Collider, our journey has been one of measuring, questioning, and discovering. We learn that balance is not always perfect, and that imperfection is actually the reason we are here today. Life exists in the margins of asymmetry, a beautiful exception to the rule of mutual annihilation. The universe is vast and strange, but it is our home, and we are its way of knowing itself. You are part of this story, made of the same ancient matter that survived the dawn of time. Thank you for spending your time with us, exploring the deep questions that define our reality and existence. This is Astrum Discovery Network. Remember to like and subscribe for more journeys into the unknown. Goodbye.